very happy to welcome Professor Abbadi. Merci.
Good morning, and thank you very much for this very kind introduction. Yes, I should say that my background is databases and distributed systems. I'm very excited that this forum now is bringing in lots of different communities together, and we are talking about a common data structure or a common challenge. In this case, it's blockchains. And I believe there are lots of interesting routes where this comes in from. So what I'm going to plan and doing today is to try and give you a high-level perspective of how many of these things come together. You'll all probably know a lot of the details, but I hope this new kind of look at it might give you a different vision of how things are going. I will also concentrate more in the second half of the talk on attempts to provide scale and higher throughput in blockchain systems. This is work that I've done with my colleagues, with my colleague Divi Agrawal and several of the students, Mohammed Amiri, Sujaya Maya, and Victor Zakhari. So we all know that we are here because of blockchain, and it has been like capturing the imagination of everybody. I mean, it's kind of surprising. You have Newsweek talking about blockchain. There was an article in the New York Times a few months back about electronic voting and how it needs to use blockchain. And when you look at the article and you read the details of the article, this is an opinion article just for the general public. They are talking about forking, double spending, mining, a lot of technical details that are now in a regular political newspaper and you are expecting the general populace to understand and know. So it's kind of infiltrating into our conscious, whether we like it or not. And that's quite interesting and challenging. One very important aspect is to realize that a lot of different things are coming together in different ways into this new data structure. There is a lot of distributed system. The language is very familiar. We talk about consensus. We talk about replication. And then there's the database world where we also talk about replication. We talk about commitment. We talk about all of these different things in slightly different terms, and yet we are trying to merge it all together. And what is our goal? Obviously, we are having to do this in an environment that is driven by economics, by various assets that are being traded. And this was one of the original kind of raison d'etre for databases, is how to execute transactions atomically in a fault-tolerant way. That's kind of where it all started from. So where is it now? Come in the security aspect, which I think is very important, especially from a database world where most of the time we worked in an environment where we trusted the servers. We believed that the servers were under our control. So we have fault-tolerant protocols, lots of them, but they usually looked at the fault tolerance from a crash point of view, from a fail-stop point of view. This is unlike the distributed systems world where there was a lot of talk about Byzantine failures and maliciousness. It's the intermingling of all this that I think is driving and is going to help us evolve and develop other different interesting protocols and understanding. So I think a forum like this is important because I usually just go to my database conferences, and coming here, you hear a lot of different things that help understand different points of view. So let me just give you a big briefer on Bitcoin and blockchain. Assuming originally we had these big trusted banks. You know, this is, we built these big banks. They are in Paris, you'll see big structures, stone structures that we all trust. They exhume trust. You see them and you say, oh, I can put my money there and it will not go bad. It will stay there, and if I want to do something with it, it's going to be still variable. What happens with Bitcoin is we say, no, we don't want to trust these banks. We actually don't trust them. We are skeptical of them. What are we going to do? We are going to trust everybody. So we are all going to be in this big peer-to-peer network where we are going to communicate with each other. We're going to trust each other, put our money, our assets with each other, and we will be checking on each other. Okay, so that's one aspect of the Bitcoin blockchain world. Another aspect is how do we transact with each other? This is, again, quite an old notion that has been around, and we are all used to checks, for example. You write a check, and I, El Abbadi, write a check to Sarah, and I sign it. So signatures are very important. And they have been important for a long time, and what we are doing now is we are just using them in a different context. We're not only using signatures, we're using them to identify ourselves with. So my public identity becomes my public signature, and if I want to sign something, I use my private signature to communicate with somebody else. On the other hand, we have transactions. With a bank, I take my check, I sign it, and the bank keeps track of everything that has been happening. We have ledgers and the logs of all the transactions that have been happening. This is what a blockchain is. It's basically a history of all the transactions that happened on a particular piece of coin or on an account. We also have the issue of concurrency has been foundational in the development of distributed databases. How do we make sure that different transactions that are accessing the same data, so they are conflicting, and they are potentially accessing the same coins, the same structures, how do we serialize them? How do we make sure that they are executed in a total order so that everybody agrees on this order? This is the problem of concurrency control. We have the same problem to solve in a blockchain environment and in a Bitcoin environment. We have a problem of atomic commitment. When do I know that a value has actually been committed? When it is deep enough in a chain. Well, this has been a problem that we have been dealing with, but we've been looking at it from a narrow perspective, from a perspective of failures, of crash failures in particular. And what this world is forcing us to do is to say, hey, we are not living in this simplistic world. We have to move on to be able to interact with each other in a non-trustworthy environment where we don't have this big trusted bank. Rather, I'm trusting that collectively all the people in the room together will be doing the right decisions. So in a way, we have, you can think of the blockchain architecture as having different nodes. Each of the nodes has a full copy of the chain, so there's full replication. And on top of this, we are executing transactions. We have transactions that are trying to be inserted into these blocks to execute transactions. And who's going to do them? The miners. The miners are going to do this to make sure that there is no conflicts between different operations. That is the concurrency, the role of the concurrency control. So it's instructive to kind of look at what is a transaction in a blockchain world. So here is one model for a transaction, is that a transaction takes multiple inputs, and it might be different parts of Bitcoins that I accumulated, and then I together merge them together and give it to Bob. So Alice has three different pieces of Bitcoins. Collectively, these are the input. Think of them as read operations in a transactional setting, and then they are written to Bob where they are being given to him. Alternatively, you could have Bob breaking up an asset, a particular 1.8 Bitcoins, and splitting them and doing two write operations. So it does a read operation and then write operations. In a blockchain setting, we have multiple blocks that refer to various assets that each of the individuals have, And collectively, you have to make sure that in the validation phase, when I'm doing the concurrency control in the validation, I know that I have all these assets and I can collect them together and add them to, give them to Carol, for example. Alternatively, Bob could sign them and split them and give them to somebody else. So we have all these transactions that are reading objects and writing objects, and this is continuously happening throughout the lifetime of the blockchain as operations happen. We are living in an untrusted world, so we need to have tamper freedom. So how does blockchains do this? They have the blocks, and each block has a bunch of transactions, and there are pointers between them, but they are not normal edges, normal pointers, they are hash pointers. Each block hashes the previous block and maintains that value. So if anybody tampers with one of the blocks, this can be detected easily. This is different from a traditional log where I put all my operations in the log and I assume it's just an append-only log which maintains the structure, and we are not worried about it being tampered with. The big challenge is how to make progress. So we have a blockchain, and I would like to add a new block. So this is basically what you have to do. You have to make sure that you are validating the transactions. And here we have to do two kinds of validations. We're going to validate the transactions within the block so that they are not conflicting with each other, as well as consistent with the previous history that we have across the blockchain. So the network needs to agree together on the next block to be added after doing this validation. So there's a validation process, and there's the actual ordering of the transactions and putting them into the blockchain. As multiple people talked about before today, there is the reward, which is the incentive for the miner to move forward. So now who is going to add this new block to the head of the chain? This brings up the consensus problem. So the consensus problem is we have all these different miners, all these different nodes in the network, each of them wanting to add a block to the end of the blockchain, to the head of the blockchain, and we need to agree with each other on this. This is the classical problem of consensus. Traditionally, all participants must be known a priori. We must know who are the participants to execute the consensus protocol. The consensus protocol traditionally was done using communication. You exchange messages, multiple rounds of communication, and eventually you agree on who is going to add it. Knowing the number of participants is very important. All the protocols depend on a notion of quorums. Majority, 2/3, whatever it is. So this is what gives us the bifurcation in the world of blockchain. We have permissioned and permissionless, open, closed. And most of the talks this morning were about the open model, where it was permissionless. So anybody can go in, anybody can go out. And this is the world where we do not know the number of participants. And that's why we have the solution of going to don't communicate, but intrinsically have each miner do work by itself without communicating with others to solve this puzzle that is going to make me qualified to add to the head of the chain. This is a radically different approach in the way of thinking about the problem than the traditional approach. That's the proof of work, and there are alternative proposals. I will just live in the Bitcoin world for the purposes of this talk. In a permissioned world, you know the number of participants. So now we can use the traditional approaches, and it's interesting because we do it in a world that is not trustworthy. We don't trust the participants. So we need to work in a world that assumes Byzantine agreements, and there's the reason to use Byzantine fault tolerance in this context. So the two different approaches differ in that respect. Bitcoin has several limitations, and in particular, the throughput or the latency is very slow. We know that you cannot, by design, add another block except every 10 minutes. So as a result, there is high latency. We also have a problem of throughput. You cannot have much, the size of every block is limited to 1 megabytes. We have a problem with how to increase the number of transactions. If you look at a database world, we cannot live with numbers of 10 transactions per second. We need to go to thousands, if not millions of transactions per second in an economic environment where things are happening all the time. So how do we push forward and move into a world where we can have more transactions? There is a tension that's continuously happening here. This is a problem that has been studied over the last few years. And obviously there is the obvious solution. Well, why did you limit yourself to the size of the block? Why did you limit the 10 minutes, the rate at which you can generate blocks? So we could move into a world where we increase the number of blocks or decrease the block interval. Well, there are some interesting explorations of this, and this has been studied in the literature and verified. I could take a block which is being generated every 10 minutes, 1 megabytes, and instead of that, 10 times the block. So instead of 1 block every 10 minutes, I'm going to generate 1 block that is 10 megabytes instead of 1 megabyte. This would increase my throughput from 7 transactions per second to 70 transactions per second. Obviously, I can do even a bigger block and get 700 transactions per second. Maybe I can even move on to a much bigger environment, but this is not an appealing solution. Why is it not an appealing solution? It decreases fairness. Originally, blockchain had this very democratizing approach where anybody should be able to do the mining and anybody should be able to add a block to the chain. By increasing the size of the block, we are giving larger miners a significant advantage. There's also a second important aspect, which is that it requires a lot more storage and requires a lot more network bandwidth. You have to be pumping out, after a new block has been added, a huge blocks out into the network. So this approach is not appealing. Alternative approach is to say, I'm going to decrease the block interval. So instead of 10 minutes, we'll decrease it to 5 minutes, and I'll double the transaction throughput. I'll decrease it to 1 minute and have 10 times. Actually, the discussion about the gap theorem this morning, the gap that is actually touching on this problem, because what's happening now is I will take less time to actually execute, to generate my new block. Problem here is that it becomes an easier problem to solve. So I'll increase the number of forks in the network. Increasing the number of forks results in instability in the network. When do I know that a transaction has committed? Typically, we wait for a longer time. For example, 6 blocks. If I increase the number of forks, I will reduce the hardness of the problem. I will increase the number of the forks in the system, and then the performance of the whole network will be unstable. So there have been various approaches to try and solve the scalability problem, and what I'm going to do now is it'll give you a high-level description of various approaches, and I'll pick on 2 or 3 different mechanisms that have been proposed. Each of them has a lot of different aspects, or are a lot more complicated than what I'm describing. But I will focus on one aspect for each of them and try to highlight what they were trying to do and what they were bringing out from a throughput point of view to increase the performance point of view. Most of them try to use Byzantine fault tolerance, so a communication-based approach that assumes you know the number of participants to solve the problem. This is in a permissionless world. So this is an environment where I don't know the number of participants, but they're going to try and use a subset, committees, to create agreement on the next block, so to increase the throughput. So let me remind you, abstractly, the mining problem is that we have blocks and chains all over the world, and somebody has created a new block and is going to try and win the consensus problem to distribute it to everybody else. So if I win it, I'm going to add this block and broadcast it to the rest of the world. So just as a refresher, practical Byzantine fault tolerance, which is one of the main building blocks that is used in many of these protocols, was proposed by Liskov et al. In 1997. And the goal is to implement a deterministic replication mechanism in an environment that has malicious failures. All of these protocols are working in an asynchronous environment. It makes no assumptions about the faulty behavior and puts no bounds on delay. So it's an asynchronous system and guarantees safety in an asynchronous world. If you put some bounds on communication, it will guarantee that eventually you'll have liveness. Byzantine fault tolerance assumes that the number of participants is known in advance and is an expensive protocol. It takes several rounds, and it requires quadratic communication. So n-square communication if you have n participants. This can grow very fast. And as we've been saying, I am looking at an environment where the number of participants, the number of nodes is huge. So there's a challenge here. And every node must multicast its result to everybody. So there is a tension here that needs to be solved in these permissionless world. So I'll start with Bitcoin NG, which was a proposal from Cornell. And it makes an interesting observation. It separates the role of validation from leader election. So there are two aspects. When you are elected as a leader, you have to do two things. You are going to validate all your transactions, as I explained before, and you're going to add this block to the head. So there is the fact that I won and the fact that I can do the validation. So I have a miner, and the miner basically receives a bunch of transactions continuously. And as it's doing this, it is doing the mining, and eventually it has a block and it's doing the mining. And as it's doing the mining, it figures out that there's a nonce that is going to solve the problem. And once it has solved the problem, it succeeds and decides that I am the successful miner. And so what's happening here is that I'm collecting transactions from the past continuously. And once I have this set of transactions and I have won the consensus, I've done the mining correctly, I've solved the puzzle, I can add it. So it is retrospective. It is taking transactions from the past, from the last 10 minutes, and adding them to the block. What Bitcoin so here is another way of looking at it. This was the last winner. This was the last block. I have a bunch of transactions that are coming in the system. There's the miner working and getting transactions as it is working. And eventually, as transactions come, it is trying to solve the puzzle continuously, and then it adds all of those. So the serialization of the transactions is happening from the past. I get the transactions and then I serialize them and I figure out that this is the order in which I'm going to execute them, and I put them back there. In NG, what they do is they actually reverse the problem. They are going to be forward-looking. I get elected, and hence I'm going to install the transactions that I'm interested in. So it's forward-looking. You get elected, and you know you're going to be elected for the next 10 minutes. Now I can generate blocks of transactions much faster because I am the leader. I am just the sole leader in the world. So I can add those transactions to the blockchain. So I can add more transactions so you can have better throughput. You don't have to solve the puzzle every time you add a bunch of transactions. So here is a miner. The miner has been elected. They've solved the proof of work problem. They've become the leader. Transactions come. As the transactions come, they are put into blocks and added to the blockchain. And I can do this much faster. And then somebody else becomes the leader, and I give up, and somebody else wins, and so on. So we have key blocks, which are crucial for election, and that uses proof of work. But then you have micro blocks, which have transactions, and those are just signed by the leader, and that's all that needs to be done. So you can have a much faster throughput that is going on. So in a way, we have two kinds of blocks. We have key blocks, and then once you are the leader, you can generate micro blocks, and they can continuously be generated. And it's the leader who generates those micro blocks. They sign them, and you move on. So each block is signed by the current leader, and the problem is there could be a malicious leader. So once you're elected, you could be malicious, so you can generate more forks, especially micro blocks. So that's a challenge which needs to be addressed. So I'll take another work which was Bizcoin, and that's a proposal. It was from EPFL. And here it uses a very similar approach. I'm going to focus on the aspect of increasing the throughput, where instead of trusting just the leader, so this was the picture we just had before, where the leader was the one who was generating the microblocks. Instead, they're going to create a window which is going to be the last K leaders that were elected. And they need to collectively execute an agreement protocol, PBFT, to solve this. So now we can tolerate malicious behavior as long as we are within this block of processes, block of miners that have won. So you'll have the leader who's going to be proposing a new block, but micro block, but by itself it cannot generate it. It has to get agreement from the collective group. So miners still use proof of work to mine blocks. You have a shared window, and there's going to be your share in the block is going to correspond to the number of times that you were successful in solving the proof of work problem. So for example, here we have the leader has 2 votes, the orange has 3 votes, and the blue has 3 votes, because in this window they have. And then they solve the puzzle. So we are still working in this environment with micro blocks, but instead of trusting the leader, we're going to have a collection of processes that together are going to solve the Byzantine agreement problem to guarantee, to restrict the maliciousness of the faulty processes. The protocol actually adds other things. They use a notion of optimized collective signing to reduce communication. Instead of using the regular PBFT, they use actually an optimization that solves the problem. Instead of being quadratic, it goes down to linear using a tree structure. A different approach which has been used in the database world especially is what's called sharding, or breaking up the work among different processes. So in a database world, you shard the data across different servers so that the work is done across different servers that can be working in parallel, and then you make progress. So abstractly, this is a proposal from NUS in Singapore. The assumption is that you break the execution into epochs. So you have a bunch of servers, and you divide the world into epochs, and then you know the list of transactions, and they have an interesting way of sharding these set of nodes. They use a randomization algorithm that partitions the nodes into committees. So we have various committees. So we take the original set of servers, they are sharded into different committees, and they are partitioned into different committees, and then the transactions in the system are going to be distributed among these different committees. Assumption that they make is that the transactions are only focusing on operations or coins in that particular shard. So the work is distributed among different committees, and they are going to have to work together to mine the blocks. So within each, so we'll have different committees, and each committee is going to get a set of transactions. So you have different, let's take this example. We have two different committees. They're going to get two different sets of transactions. They're going to execute Byzantine agreement protocol on each of these particular set of transactions, the sharded transactions. Once they have agreed on, each of these committees has agreed on whatever it has, they create a digest which summarizes what is in them, and then they send it to a final committee that collects all the information from the different committees, takes the set union of them, and the assumption here is that there is no transactions that are crossing different shards. That's an important assumption they make. And they do a digest, and then you execute Byzantine agreement here. You agree on the total order that's going to happen, and you send this back to all the participants, to all the committees, and all the participants in the system. Everybody here is sharing the same blockchain, and the final committee now is making sure that you add a block to the end of each of these blocks. We're just sharding the work, so we are doing the work in parallel. It's giving them improved performance. There are improvements on this work, but the basic idea is the sharding. So we have different ideas that we've seen up till now. We've seen, where do you do the transactions? Do you execute them from before or after? How do I do this? And the notion of sharding. This is all still within the permissionless world. So I'd like to explore a little bit more this notion of sharding in a permissionless world. Let's consider a blockchain environment where I have all the nodes or all the miners that are distributed on a peer-to-peer network. And instead of keeping the blockchain as one unit, I'm going to shard the blocks within the blockchain. Within each block, I'm going to shard it. So you can look at each block and say, I have a blue, a red, and a green, and the orange. And I'm going to break it up and break the miners themselves also across, I'll partition them and distribute the work among all of these different miners. So now I can have 4 blockchains in this example running in parallel, doing the mining in parallel, and hence increasing the throughput, hopefully. So what are the types of transactions that I have to deal with? I might have transactions that are solely within each of the blockchains. So for example, I have transactions that are single sharded transactions. So all the red transactions, all the yellow transactions, blue transactions, and green transactions. Those there's no problem with. Every miner can take any of these transactions and verify them and execute them, and everything looks good. Problem is that, as I alluded to before, I might have cross-shard transactions. I might have transactions that go between the green and the red. I have transactions that go between the blue and the green. So now we need to have, and I'm thinking of this from a database point of view, I will need to have atomic transactions that are crossing different servers. This is an old problem. This is commitment problems that we've been looking at. Well, this has also been explored in the blockchain world. And there are cross-shard transactions. For example, there was this recent work by Hurley in just last PODC, which was based on an earlier blog in Bitcoin, actually, from 2013. Abstractly, the problem is that I want to do what I just described. So, but it's explained in terms of Bitcoins and currencies. So I want to do cross-chain transactions. I have Alice and I have Bob, and one of them has, Alice has some Bitcoins and Bob has, Alice has Ethereum and Bob has Bitcoins. And what they would like to do is they want to exchange them. So so Alice wants to give Bob her Y Ethereum, Ether, and get back X Bitcoins. And it needs to be done in an atomic manner. So you want to be able to give to Alice the Bitcoins and to give to Bob the Ether. We need to do this in an environment that is tolerant to failures. Hurley and Nolan's solutions make assumptions about fairness and what happens if a failure happens and who should be hurt. What we need is an environment that is strictly the all or nothing environment, where if a failure happens, if Alice is not acting fast enough, I still should be able to allow her not to lose her money. And so there is need in this world where I'm trying to execute transactions to have a notion of an all or nothing across different transactions. And we are currently working on solutions to this, and there are other proposals that are that have been proposed recently. These are interesting because they are going to help me solve the throughput problem. If I have these cross-chain transactions, then I can execute the transactions in parallel across different miners and get the throughput even when I have cross-shard transactions. In the remaining time, I'd like to switch to another universe, which is the permissioned universe. So in the permissioned blockchain world, we know the number of participants in this world, who are participating in this blockchain. So let me remind you of the Bitcoin process. We have a client, and the client broadcasts its request to all the miners. The miners validate the transactions and put them into blocks and try to solve the puzzle. Eventually, one of these, P3 in this case, wins. He solves the puzzle. So notice that first we have we need to validate the transactions, and then after the validation has happened, you're doing work to order. In Bitcoin's case, we are doing it using mining, proof of work. After that, the winner is going to send it to everybody. Now everybody has to revalidate to make sure that the miner is correct and that they are executing, that they are not malicious. Once that has been done, the transactions are deterministically executed, and now we know that all the blocks are identical and have the same results. So one can call this an order execute architecture. I am ordering, it's the classical approach. I'm a set of transactions together are trying to order the transactions, whether they are using it in the Bitcoin approach, they would be using mining. But if I move to a permissioned world, they would be using a PBFT. They would be using a consensus protocol to solve the problem. So we have an ordering, and then you have deterministically validation and deterministically executing all the operations. If there is non-determinism, we end up with forking, and we need to deal with this problem. This approach is a sequential approach, and it can cause bottlenecks. That's the challenge. So now how can we approach this in a permissioned world? So traditionally in databases, there are two approaches to the problem. One is the pessimistic approach, and one is the optimistic approach. So there is the execute order validate proposal, which is Hyperledger Fabric approach, and a set of applications are run concurrently. So we have different applications, so this already gives me some parallelism. And each transaction is first executed, it's executed, and then you decide on the order in which things are going to happen. So the execution happens first, then the order is determined, and finally you validate that the executions are done in the same order. So this is like in an optimistic approach. You execute the transactions first, and then you do a validation phase at the very end to discover if there were conflicts between different transactions. And if there were, you might abort it. Otherwise, you'll commit it. And in an optimistic world, it usually gives us much better performance, optimistic versus pessimistic, because you don't pay the overhead of all the locking and the pessimistic approach, which holds on to things before. So Hyperledger Fabric has been proposing this approach. They basically use an execute order validate architecture. They increase the performance by having multiple transactions, multiple applications executing in parallel, and they allow non-deterministic execution because they can detect if there is a problem. How do they do this? They have 3 different types of processes or nodes. They have clients that send transactions. They have endorsers who are going to execute the operations and verify that they are correct. So they execute them, and they could be executed in a non-deterministic way. And finally, you'll have the orderers who order the transaction, the blocks, and figure out the final order in which they're going to be done. And then they are sent back to be validated by the endorsers. So here is a schematic of what is happening. So we have 3 different applications here. I have the Alice, the green application, Bob, the blue application, and Charlie, the yellow application. And I have a set of orders. Everybody, all the endorsers have the blockchain. And we have the transactions are generated by Alice, Bob, and Charlie and are sent to the endorsers. The endorsers execute them and return the answers back to the clients. The clients have a policy. They decide on whether how many of the different endorsers need to actually, for example, I can tolerate 1/3 of the endorsers being wrong. It can also handle the non-determinism if there are conflicts in terms of what is being reported and so on. They create a block, and each of them sends it to the orders. Now there is an executed set of transactions that have been created, and they are sent to the orders. The orders execute Byzantine fault tolerance. Actually, it's pluggable. You can, if you want to assume that there's only crash failures, you could use Paxos. And then the result is sent back. The order is sent back to all the endorsers who verify that the execution is consistent with what was happening before. Clearly, if there's no conflicts or very few conflicts within an application and across applications, this is actually going to give me good performance. If there are conflicts, it needs to be detected at the validation phase. So if there are lots of transactions, if there's a lot of contention, we're going to have a challenge here that needs to be detected and aborted. So if there are, for example, a new block that has been created, and let's assume that on the top right, we have several read and write operations that are executing on the same records. So the blue and the green and the orange are conflicting with each other. Some of these blocks would be, or these transactions would be aborted. So as a result, we end up in an environment where it will give good performance in a world where there's little contention, but if there's high contention, we're going to have a problem. We're going to have reduced performance. So we've been working on injecting some ideas, again, from databases by introducing a notion of a dependency graph, which is a traditional data structure that is used to understand when there are transactions that are conflicting, i.e. when you are reading from another transaction and ensuring that this order is maintained. So for example, here I have a bunch of transactions that are reading and writing different objects. And now I'm going to have a dependency graph that reflects when a transaction reads from another transaction or one writes something that is written by another transaction. Given this dependency graph, we can go back to the original approach where we do order execute, but now I'm able to do parallel execution because I have this dependency graphs that are going to help me solve that problem. So I'm reversing back again to instead of the Fabric approach, which was to execute and then order, we're going back to the Bitcoin approach, which was the order execute. And here we have, again, a set of distributed applications that are running concurrently. We have a bunch of orderers who order transactions and put them into blocks, but generate a dependency graph for the block and multicast it to all the nodes. Each transaction now can be validated and executed by the executors following the dependency graph. So we are proposing a system called PARBlock, which basically follows the order execute approach. It supports parallel execution, and it detects conflicts and incorporates it into the execution order. There is an issue with non-determinism where we are, unlike Fabric, we will have to abort the transactions that result in non-deterministic behavior later on. So depending on the application, this might be a good idea or not. So here is an example where I have a bunch of clients. I have the orderers and I have the executioners. And the different clients generate various transactions. The transactions are sent to the orderers. The orderers are going to execute BBFT or Paxos, depending on where you are heading and what is your failure environment. And then it generates critically the dependency between the different transactions. This dependency graph is now sent to the executioners who are going to order them in the right order that is consistent with the dependency graph that you are getting. So abstractly, there is this optimistic versus pessimistic approach for executing transactions. We can support non-determinism, or we can support high contention environments that have lots of conflict. So Hyperledger executes transactions first, and so it can detect when there's where there is a non-determinism and avoid executing the order and then aborting them later on. However, because there is conflicting operations, during the validation phase, you might have done all this work ordering transactions, but resulted in a failure and an abortion of transactions. What we are proposing is PARBlock, which validates the non-determinism. So it validates non-deterministic executions last. So if there is non-determinism, it's going to be detected at the very end because you're getting different answers, and that is going to be, we do not detect it early like with Fabric. However, in an environment that is deterministic, but you have lots of contention and conflict due to the dependency graph, you can detect the problems and execute them, and you'll get better performance. So it's a trade-off which is interesting. So I think I'll finish here, and I just would like to say that there are lots of different aspects to blockchains, and especially the global aspect, the large-scale replication, that requires a collective effort from different communities. And it is important to have conferences like here where the various communities meet. So it's not only a problem that is distributed systems. Yes, I've talked about consensus, and that is a traditional distributed systems. It's not only a database world where I've talked about replication, talked about commitment, all of these issues. There's an underlying aspect which is critical for the running of this whole thing, which is the security and privacy. And I don't think we can ignore the strong economic effect on this. I'm least familiar with the economic aspects of it. This is why I'm coming here, and I think it will be interesting to get your reaction to what I've been talking about. And thank you very much.
Could you briefly comment on the security trade-offs that these different constructions give, and whether they are less secure than Bitcoin, or they assume they have stronger assumptions about how weak is the adversary?
So you are talking about the first part of the talk where I talked about the permissionless work. So those are the same as Bitcoin, actually, in terms of security aspects. They assume the same assumptions.
Even when we have multiple blockchains, then we have to assume that all of them are honest.
So you're talking about NG and Bitcoin. So it is the same set of assumptions. They are assuming malicious behavior, and they are going to allow you to solve that problem internally.
So I'm confused by the last set of slides that you mentioned. So if the applications are very general, how could we, like, without running it, to detect like their dependencies first? It seems that we have to apply, maybe for like very specific set of applications, we may be able to do that. So maybe I just
So that's a good question. More. So you are going to assume that you know the transactions. You need to know what is the reset, what is the write set of every transaction that is executing in this setting. So that you order them, and then later on you verify that the execution was consistent with what you were assuming. Does that answer your question? No.
Yeah, it just seems that, so like these applications will be applied to, for example, like there's will be a particular like Hyperledger that is used for a specific type of applications, so that we kind of know their structure very well, so that we can kind of figure out the dependencies without running the transaction. But it just seems like if we want to build a system that is very general, that maybe actually going to be very hard.
So if it's very general, meaning I don't know what is being executed and what the transactions, you're correct. But in general, we can assume that you have a framework in which you know what are the transactions that are being executed.
Thanks.
I'll just shout out. Thank you for the presentation. I just have a quick question related to your first part of the presentation. We talk about solutions to scaling in the particular case of Bitcoin NG. Coming from a non-computer science background, my impression is that the leader selection part is the difficult part, at least for Bitcoin type of transaction. The validation part is kind of easy to run. So in that sense, separating the two and taking a forward-looking approach, I didn't quite get what exactly do we gain on the validation part, because the selection part is still a proof of work based.
So now once you are elected as the leader, you can generate these transaction blocks very fast. You don't have to, you are the leader. You don't, so the problem with Bitcoin is your new block is a function of the contents of the block. So the mining is a function of the blocks. In this case, once you've been elected as a leader, I can generate these micro blocks as fast as I want. It's a separate process. Now, you are right. It is very easy. And that is part of the problem, is that I can now, if I'm malicious, I can generate incorrect executions. I can do malicious behavior. And that's why the following work, the Bitcoin approach, was trying to harness this problem, harness of how you can generate the additional microblocks. So when you are adding the transactions, you need to get agreement. You just don't do it immediately. So with Bitcoin, you are still doing a proof of work, so solving the hard puzzle to get elected as a leader. But now I have a bunch of different previous readers, a priori readers, that are going to collectively agree together on the set of transactions. So adding the new set of transactions, the validated new set of transactions. The leader is still going to validate them, which you're right is easy, but it's going to execute this collective Byzantine agreement protocol to add the new transaction block, the micro block in their language.
So about Bar blockchain that you presented last, it's been designed with to be resilient to high contention environments, right? Could you please give an example of such an environment? Because typically we use cryptocurrencies as examples for blockchains, but you don't have conflicting transactions in such systems. If you have, it's double spend transactions. So could you please give an example?
Yes, so like the title of the talk, this is going back to, I'm trying to move on to big data, so management of assets in general. And now you can have transactions that are, it's not necessarily a cryptocurrency. Cryptocurrency has, in an interesting way, solved the concurrency control problem by focusing on the actual units of money that we are working on. Here I'm thinking of an environment where we are trading, we are executing regular transactions, so read and write operations that are going to read various objects and write versus various objects. So it's not necessarily, it's actually not for a cryptocurrency world, but for a world where we would like to be executing lots of transactions with high throughput.
Okay, Angelo Corsaro, AT-Link. Very nice talk, thank you very much. So I would like to hear from you, well, in your talk, very nice, so you showed all tricks applied to new problem and you know, how people were, I would imagine, another variation could be leveraging ordering in sharding. It's kind of right, obvious, fine. Yet another way of improving. So my question to you is, okay, what should be next? What would be the interesting direction that you suggest a young researcher here to look at? Because that's, right? You know, interesting things that we have done in the past. There are lots of hat tricks that we have, right, coming from distributed system, databases, and sometimes you need just to give them a twist to apply them in a new setting. So your intuition, where does it bring us? What should we look next? Thank you.
That's a difficult question.
I only do difficult questions.
It's the last one, by the way.
Yeah, so the hype about blockchain, I believe, is twofold. There are two aspects. One is the cryptocurrencies, but there's also the big potential of using blockchains for managing regular large-scale data in, you know, supply chain systems, in all these type of systems. In those systems, there are aspects that I believe are differentiated from the cryptocurrencies. And I think your question touches on that also, is that we actually have various objects that are being executed. I touched on a problem which is the cross-chain transactions. The cross-chain transaction problem, in a cryptocurrency, you're just taking one type of coin and exchanging it for another. But if I have an environment where I have multiple blockchains for different applications that I'm trying to execute among them, that is where the challenge is. I also believe the fault tolerance problem has not been very well addressed in the Bitcoin world. We deal with the maliciousness, but what about the failure, especially in a permissioned environment? In a permissioned environment, you have less participants and each of them could fail and you could lose some entities. What if a client has started a transaction and then fails and then comes back later on? It's this merger between the different models that I'm hoping. I can't answer more precisely, but I'm seeing the merger of the, from my point of view, the traditional database world model, which we have transactions that read and write operations, and accessing data that is across, that is highly replicated, and we need to deal with it. Before, we were looking typically at smaller replications. Now we are looking at large-scale replications. It's this tension that I find interesting, and I'm hoping.
So thank you very much. Thank you again.